In an earlier slide, we practiced drawing Lewis dot structures for molecules, and recall that we looked at the number of valence electrons that any atom had and combined all those together and came up with a dot structure so that every atom except hydrogen had 8 electrons around it, and hydrogen, remember, can only have 2 electrons around it. And we're going to take that idea and go a little bit further and talk about the fact that covalent bonds result from electrons' orbitals overlapping. And we had seen the shapes of several orbitals in an earlier chapter. Remember, an s orbital is spherically shaped, and again, there's no boundary there. This is 95% probability of finding the electron in this region. So an s orbital can overlap another s orbital. So this is like a Venn diagram. That's where the overlap would be. And that's what constitutes a bond. And we might think, since electrons repel each other, that two atoms wouldn't want to share electrons, but the electrons on one atom are attracted to the nucleus of another atom. So this still is a positive attracts negative idea. So an s orbital could also overlap a p orbital. So if the p orbital was oriented along the x-axis, if we call the number line the x-axis, we could have overlap there. An s orbital may not necessarily overlap a p orbital in the y direction. So that probably wouldn't give us, even if I drew that a little closer together, this would not be a very good physical overlap. And what we're going to look at is a new theory that describes identical bonding that we see in molecules. And I'm going to go ahead and mention this here. If we have two p orbitals, if this was the nucleus of one atom and the nucleus of a second atom, the p orbitals can overlap in this fashion. So that's going to be a very special type of bonding, and when we get to that, we'll call this pi bonding. And again, a p orbital in this direction probably could not overlap a p orbital in that direction. And because those wave equations, Schrodinger's wave equations, describe shapes of electron orbitals, those are physical three-dimensional shapes where we're most likely to find an electron. Those shapes have to be able to physically overlap in order to have a bond. So the theory that we're going to look at is hybrid orbital theory. If we recall from an earlier chapter, if we look at a carbon atom, carbon is on the second row of the periodic table. It has a total of 6 electrons. It's in group 4, so it has 4 valence electrons. If we drew the orbital diagram, we call that a 1s orbital, and then 2s, there are 3 p's in the 2p subshell, 3p orbitals, and we would put electrons in lowest energy first. 1, 2, 3, 4, 5, 6. So carbon's 4 valence electrons that get involved in bonding would reside in these orbitals when carbon is just an atom all by itself. And since the s orbitals are spherically shaped and the p orbitals have the odd shapes like this, atomic orbital theory, so these are atomic orbitals. These don't give us a good argument, so to speak, for why we see identical bonds in a carbon when it's combined with other atoms to form a molecule. For example, methane, the simplest hydrocarbon, CH4, if we draw this dot structure, the dot structure and the electron repulsion, those theories help us discuss the shapes of the molecule. But if we know that there are 4 identical carbon-hydrogen bonds in methane. They're the same bond lengths. And we cannot explain that with the different shapes of the s orbitals and the p orbitals. So this is not explained by atomic orbitals. So we're going to look at, on the next piece of paper, hybrid orbitals, and hybridization of s orbitals and p orbitals give us hybrid orbitals, and that does explain identical bond lengths that we see. So I often tell my students that scientists aren't happy just saying, oh, that's nice. There has to be a theory or a reason to explain what we see experimentally. So hybrid orbital theory, sometimes a textbook will make it look confusing, but hybrid orbital theory does explain the identical bonding that we do see in molecules. So hybrid orbital theory is focused on the central atom. So we are only looking at small molecules, and the number of electron domains is critical in order to determine how many atomic orbitals are going to be hybridized to create the hybrid orbitals. So the number of electron domains we talked about on an earlier slide. This is around the central atom. So I'm just going to write this. The number of electron domains is going to equal the number of atomic orbitals. I'm going to say used. We talk about it as though we're creating the orbitals. The orbitals are already there. This is sort of a bookkeeping system. So that's going to be the number of atomic orbitals used to create, again, we're not really creating anything, the same number of hybrid orbitals. So I usually abbreviate hybrid orbitals with HO. Do a lot of abbreviations in this theory. Atomic orbitals I call AO, and then the number of electron domains around the central atom is ED. So if I look at CO2 as an example, the dot structure for CO2, we end up with 2 double bonds around the carbon, and we don't really care about the outer atoms, lone pairs. We're going to focus on the central atom. So there are 2 electron domains around this carbon. So we're going to use 2 atomic orbitals, AOs, and there are always 1s plus 3p orbitals available. If we're on the 3rd row of the periodic table, then there are d orbitals available as well. So we're going to use 2 atomic orbitals. I generally put a box around those. And we're going to create 2 hybrid orbitals. And they're going to be called sp hybrid orbitals because we use one s and one p orbital. So those are the hybrid orbitals. And just like hybridization of plants or peas, peas as in garden peas, the hybrid will have characteristics of both. So if there are two, an sp hybrid orbital is going to be part s in character and part p in character. Remember, an s orbital is spherically shaped, and the p orbitals have the kind of look like two teardrops. So we have two hybrid orbitals. So each hybrid orbital now is identical. And then there are going to be two unhybridized atomic orbitals. So those are going to be important later for describing double bonding. So those are two unhybridized p atomic orbitals. So we're not going to discuss that yet, but that we'll come back to that later. So now we can say, well, carbon, the central atom, has two of these sp hybrid orbitals around it, and then that would explain the identical bond lengths that we see to oxygen. So I'm just going to kind of shade that in. That's an oxygen atom, and we might just put a p orbital around the outer atom. So now this overlap, this sp hybrid orbital could overlap an outer atom's orbital. We're going to do this for several electron domains. So 2 electron domains is the fewest number that we're going to have. So 2 groups of electrons means we're going to put a box around 2 of the atomic orbitals, rename 2 hybrid orbitals, and we'll come back to these unhybridized orbitals later. If there are 3 electron domains, so if I draw something with 3 electron domains, maybe sulfur dioxide, I'll do that. I've drawn that before. So here there are 3 electron domains. So remember that lone pair counts as one group, the single bond counts as one group, and the double bond counts as one group of electrons. So there are 3 electron domains, so we're going to use 3 AOs, 3 atomic orbitals. So we always have an S, there's always only one of those, and there are always 3 P orbitals, and we're going to rename 3 hybrid orbitals. So again, just so that I keep myself straight, I put a box around the 3 atomic orbitals that are going to be used for hybridization. So we're going to have 3 hybrid orbitals renamed as sp2. Since we're using 2 p orbitals, we'll have 3 sp2 hybrid orbitals. And then we'll have 1 leftover, that's easier to write than unhybridized, 1 leftover p atomic orbital, which is going to end up accounting for this double bond. So we don't want to get too far ahead of ourselves. So 3 sp2 hybrid orbitals would be around the sulfur. So if I drew sulfur, then the sp2 would still be part s in character and part p in character. And then these, since there are 3 electron domains, these hybrid orbitals would maximize the angle between them because there are electrons. We can think about the orbital as kind of a smeared out negative charge if we want. So same concept here, 120 degrees between the hybrid orbitals, and each one of these is just renamed sp2. So we have the case again where we have to make our brain not seek a pattern. So when I see 3 electron domains, I want to say sp3. So the s counts for one of those orbitals. So sp2 is going to tell us exactly what environment a central atom is in. So if this was sulfur trioxide, the lone pair would be in one of those orbitals. And then this oxygen could overlap, and this oxygen could also overlap here. So we would still have overlap between two atoms. And we'll come back on another slide and talk about this unhybridized p atomic orbital. That's going to end up accounting for this double bond. But right now we're just looking at the hybridization. So we would say that sulfur is sp2 hybridized. So 3 electron domains means 3 atomic orbitals are used, and we rename 3 hybrid orbitals. It's one of the S's and 2 of the P's, so we call that sp2. We could also have 3 electron domains and double bond. So we call sulfur trioxide, ends up looking like that. So again, 3 electron domains, so that means we use 3 of the 4 atomic orbitals. So we again have 3 sp2 hybrid orbitals on the sulfur. And this p orbital that does not get involved in hybridization is what's going to be used later to explain that double bond. 4 electron domains, for example, the methane that we drew earlier, CH4, has 4 groups of electrons around that. So 4 electron domains means we're going to use 4 atomic orbitals, S, P, P, P. So we're going to use all 4 of these and rename 4 hybrid orbitals as sp3. So this set of hybrid orbitals, we use the s orbital and all 3 of the p orbitals. And again, they basically have the same shape. They might be more p in character, so maybe a little thinner, but they still have that part p in character and an extra lobe because the spherically shaped s orbital. Then we'd have 4 of them. And these would not point out at a 90-degree angle. Remember, this would be a tetrahedral. A tetrahedral electron domain geometry. So 4 electron domains automatically means those electrons are repelling each other and assuming a tetrahedral position. So I probably couldn't draw that very well. But there would be 4 of these. So then we could try to draw carbon. I'm not going to draw that little lobe there. It just makes it too messy. So we'd have 4 sp3 hybrid orbitals around carbon. And again, this theory really came about because we can look at a molecule, X-ray crystallography, and see bond links from the diffraction pattern. And it's known experimentally that methane has 4 identical carbon-hydrogen bonds. So this theory allows us to explain that. So if we have 4 identical hybrid orbitals, then we have a good reason to explain why there's 4 identical bonds. If we tried to say, well, carbon has an s orbital around it, and then 3 p orbitals around it, and then we try to connect the hydrogens, we're going to get a very strange picture with atomic orbitals. So the purpose for doing hybrid orbital theory is just so that we don't have a theory that doesn't match what we see experimentally. 4 electron domains could also occur for water, for example. 2 lone pairs on the oxygen. There's 1, 2, 3, 4 groups of electrons around water. So 4 electron domains means 4 atomic orbitals. We make 4 sp3 hybrid orbitals. And if we're going to draw that, we might put so this just looks like a flower. I'm not trying to draw it in 3 dimensions. The lone pair would go in an orbital. So that's our oxygen. And then our hydrogen. Hydrogen just has a 1s orbital around it, so we can just draw hydrogen with a circle around it. So here's the bond between oxygen and the hydrogen. So the molecule itself would be bent, but again, the electron domain geometry has to be tetrahedral if there are 4 electron domains. We can also have an expanded octet as long as the molecule or the central atom is on the 3rd row or further on the periodic table, n equals 3 or n equals 4 or 5 or 6. So an expanded octet means that central atom can have more than 8 electrons around it. So this is possible for n equals 3 or greater than or equal to 3, I guess I should put. So any atom that's on the 3rd floor of the periodic table, remember, has an 1s orbital. The p subshell always has 3 p orbitals in it, and then we'll use up to 2 of the 5d orbitals. So on the 3rd row of the periodic table, we've got 3 L values allowed, 0, 1, and 2, and so forth. So we don't care about that. So if we have 5 electron domains, for example, SF4 has that, sulfur is going to end up with a lone pair and then 4 single bonds to each fluorine. And the electron count on this from the valence electrons, sulfur has 6 electrons, each fluorine has 7. So we end up with 34 electrons. As long as hydrogen is not in the molecule, we can divide by 8, and the remainder, so this is 4 bonds, and the remainder here is 2. This is a quick way of seeing whether or not our central atom is going to have lone pairs around it. So as long as hydrogen's not there, if our electron count is not a multiple of 8, then the remainder will be lone pairs on the central atom. So here we have 5 electron domains around sulfur. So we'll use 5 atomic orbitals. So S, all 3 of the P's and 1 of the D's. And we'll rename 5 sp3d hybrid orbitals. And recall from an earlier slide, 5 electron domains automatically means we have the trigonal, bipyramidal electron domain geometry. And I can try to draw that. We have to imagine this triangle being perpendicular to the paper, and then our 2 pyramids, bipyramidal, 1 orbital above and 1 below. So if we put sulfur here, the lone pair is going to actually occupy more volume, occupy more space. So that lone pair would assume the 120 degree positions, or these equatorial positions. We'd have a F here, F, F, and an F. If we drew this with hybrid orbitals, I wouldn't be able to do that very well. we have sulfur, and if I try to draw these like a triangle, so this again would be the horizontal plane perpendicular to the paper, and then an orbital above and one below. These would all be sp3d hybrid orbitals. So we use atomic orbitals and create identical hybrid orbitals. So they all have the same name, same shape. And then if we wanted to show, we could put the lone pair here, and then the overlap with fluorine, we might just show a p orbital. So the textbooks generally have much better pictures because of the shading, and I don't draw very well anyway. So trying to draw a hybrid orbital of a larger molecule usually ends up just looking like a flower. And so finally, 6 electron domains, that's the maximum number of electron domains around an atom. So 6 electron domains, for example, could be, what should I do? I hope this is right. SF6. You could tell really quickly. Sulfur has 6 electrons, plus 6 times each fluorine has 7. Yeah, good. So this is 48 electrons. If we divide this by 8, we get 6 bonds, remainder of 0. We knew that there would be, since 6 is the maximum groups of electrons around a central atom, if we've got 6 atoms around a central atom, we know that it's going to be an octahedral geometry. And more importantly, we've got hybridization will be sp3d2. So we'll use 6 atomic orbitals, 6 AOs, and rename 6 sp3d2 hybrid orbitals.